speech. Anyway, so the target of this little primer, I will call it a primer. It's not really a course, more like a primer. Is to teach you like some of the principles, so that you can go and figure out your own mental map of how to write optimized Solidity. So the thing about the Solidity compiler is that because it's based on stack, the EVM is a stack machine. It's not a register machine like x86. So a lot of optimizations have to be written from ground up. And the compiler focuses on achieving correctness first. And when resources permit, they might add a bit of optimizations here and there. So it's not as mature as like stuff like LLVM. But you can go pretty far with what we have right now, if you know some tricks. Okay, so there are some prerequisites. It's easier to follow if you already know how to write, test, and deploy smart contracts in Solidity, or at least you have some idea of how to ask ChatGPT or Grok to teach you, maybe craft a curriculum for you. Okay, so when it comes to optimization, I think a good meme to describe it is kind of like an iceberg. Like everyone would normally they will start with the most basic, like unchecked arithmetic storage packing. Storage packing is one of the most I would say lowest hanging and most overpowered fruits, because in the EVM, when you write a new storage slot, the S store, each S store costs 20k gas, and in the future it might even increase because state access is the bottleneck in the EVM. Then you will go to stuff like maybe you place your arguments in core data instead of memory. You tweak the optimization runs. You somehow use some kind of storage packing to make sure the variables are in warm storage. You mark your functions as payable so that it doesn't have the message dot value not equals to 0 check in the background. Then you use efficient data structures, learn how to avoid stack too deep, all this stuff. And once you want to get past get under the water, which I say is inline assembly, then things start to get interesting. And some of these are not actually inline assembly. For example, function selector mining. For example, okay, when you write a Solidity contract and it calls a function, it goes through something called the function dispatch, and it's like a B tree with each node has four nodes, 4 children. So if you are able to mine a function selector with a selector of 0x000, then it will be on the leftmost side of the tree, which makes it very the most efficient to access. And some protocols, they do that. I think Cport, they mine some kind of function selector for their most often used functions. And it's not really an inline assembly thing. It's more like you understand how Solidity works under the hood. Some of it is understanding how the memory works. Some of them is understanding the edge case of the opcodes, like how to abuse the edge case of the opcodes. For example, if I want to zeroize a memory region, I can abuse core data copy. If I want a out of gas revert, I can abuse return data copy out of bounds. Some of them is general math tricks, like using Z3 to find magic constants. Z3 is a Python program, or you can like directly write the Z3, which is a bit harder because. But anyway, there are some math in Solady that have some kind of crazy constants, and all of them are found using Python Z3. And Python Z3 can also help you formally verify some kind of, like, if you want to write a new fixed point math function and you're not sure whether it works for all the U256 inputs, you probably will use Harmos, but if you want the speed, like Harmos has some overhead. So if you want the raw speed of the prover, you will use Z3. Then there are stuff like understanding how the compounder inline the functions, understanding how the EVM works, so on and so forth. So it's like a rabbit hole. I would say you need to understand how the compounder converts your Solidity into bytecode. You also need to understand the EVM, like the EVM on a very familiar level. And it also will help a lot if you have some kind of background experience in like general computer science or general math. So there are some resources that I would like to highlight. First is my repo, solady.org. Most of my work goes into Solady these days. You also can follow me on X. I think the most top of the mind resource is evm.codes. If you know what you want, you can, this is like some kind of a cheat sheet that you will use quite often. If you use enough, maybe you can memorize everything, but I still can't memorize everything. So I think you should, ResQs is one of the top of my mind recommendations if people ask me how to get very good like ResQs, seriously. Yeah. So Jeffrey from ResQs, he took Jeffrey and his team, yeah, they took a lot of effort to write super good articles. I say even writing articles is sometimes, I would say, 2 to 3 times more difficult than inventing new math, because you need to know how to explain it to different levels of expertise. There's also Note Guardians and also Patrick Collins on Twitter and YouTube. And I think this is not exhaustive. There are a lot of more resources, but these are just some of the stuff I can recall from the back of my hand. So due to this thing being 1 hour and limited effort, like I can't teach you all the tricks I know today. There's just too much. So the idea is to tell you some principles that you can use to find your way around. And if you know these principles, maybe you can invent new tricks of your own and contribute to repos. So let's begin. Okay, first thing first is safety. Because if your smart contract gets wrecked, okay, just don't get wrecked. It's not a good thing. It's not a good experience. You'll make people lose money. You lose reputation, and you cannot sleep. Okay, let's say you have the safety down. You also want to balance performance, readability, maintainability. So one of my observations, experiences is that although I am a pretty good inline assembly dev, and the auditors we hire are pretty good at inline assembly, but sometimes if you have everything written in inline assembly, there's a lot of noise, a lot of code noise. It distracts from the overall high-level business or application logic. So you might want to restructure your code, make it less optimized so that the human side of us don't feel so fatigued. Yeah, you can be like super good, but you also have to consider like others within the limited amount of audit time. Can they somehow squeeze out as many bugs as possible? So yeah, readability is also important, maintainability. And I won't say whether high level is more important than low level, because sometimes you need to know what is in the low level so that you can architect your high level such that they can synergize with each other. But yeah, you should really, if you can, like say you're self-taught, you didn't go through like some kind of intro to algorithms class, you might want to go through one like MIT OCW 6006. It's pretty good. Yeah, because once you go through all these courses, you kind of understand like it gives you more ideas, more areas of inspiration. So I won't say like high level is more important than low level. But if your high level is good, actually high level, yeah, you can try to brute force your way with all these tricks, but someone with a very elegant math formula or elegant optimization can write some kind of unoptimized code that has a lower big O complexity. And yeah. So regarding optimization, this is the first thing is storage savings are the best savings. Like if you go to any new code base and it's pretty unoptimized, the first thing you should optimize is the storage, because you don't need to use assembly to optimize storage. You can like use smaller variables. Instead of uint 256, you use maybe uint 40 for timestamps, something like that. And you will notice that generally, the more you optimize the code base, the flatter the Pareto front gets. This means like maybe initially 90% of the gas is spent on storage. You optimize the storage away. Then maybe 80% of the gas is spent on core data decoding. You optimize that away. Then you realize that everything is kind of flat. You optimize this, you get maybe 5% savings here and there. So diminishing returns. And at this point, you might want to say, okay, maybe it's enough. I will just keep it that way. Sometimes, if you're like me, like you can think of the whole thing from the bottom up, from the bytecode upwards. You might intentionally de-optimize your code so that yeah, it's more readable. Okay, so that comes to practical aesthetics. How much performance versus readability? I would say if your deck is kind of application specific, you might want to lean towards more regular Solidity. If it's some library code, for example, you want to make a new math library, a new trigonometry library, you might want to lean more towards inline assembly. Yeah, because humans and also LLMs, we have limited attention. And if you want to somehow have the best of both worlds, in a way, you can see whether Solady has some function that solve your needs, or if it doesn't have one, you can make a feature request, explain your use case. If it's not too specific, I might help you code it. So let me go through some examples of how you can write optimized Solidity without diving too deep into inline assembly. And all these examples, they are from Ithaca's account, and they heavily abuse Solady to make it optimized. Okay, so here we have a struct. You see, all of these variables are uint 256. So 20k gas, 20k gas, 20k gas. If you want to store this in storage, it's 60k gas. We don't consider like the warm storage cost. So yeah, minimum 60k gas if you do it the regular way. But if you somehow know about this thing in Solady called the byte storage, and you know about this thing called the CD compress, you can combine both of them to squeeze this struct into a single slot for the majority of use case. Like most of the use case, they'll probably use like 32, the timestamp maybe until our end of life, it will be maybe 32 bits. Hopefully we can see 33 bits. Amount, I think most ERC20s, you can fit under 64 bits. Most ERC20s. Yeah, same. So 64 plus 40 and plus 8 bytes for 8 bits for the length. Yeah, everything can fit in one slot. So you don't need to write any assembly for this. If you know Solady has this function, you can just use it to squeeze auto pack your storage. Then you don't need to decide, oh, maybe this one I need you in 40, this one I need you in 256. You just let CD compress figure out the stuff for you, like magic. And I think for DeFi protocols that want to make it as general as possible to fit you in 256, yeah, you can abuse this CD compress. Okay, so another thing about you can abuse Solady to do efficient hashing. For example, you want to calculate a EIP 712 hash. The regular way is you make a loop, you do ABI encode keycard 256. The problem with this is that there are so many overheads, so many hidden overheads that Solidity inserts. For example, if you use new bytes 32 array, Solidity will make will create some code to zeroize the elements. But we know that we don't need to zeroize the elements because we'll be overwriting it in this loop. So yeah, efficient hash leap has a function to help you allocate an array without zeroizing the elements. We know that when you use cause array access I, Solidity will emit some, I would say, out of bounds checks. And we know that this can never get out of bounds because of the loop. So you can use some optimized functions in Solidity for that. And efficient hash leap doesn't allocate memory when you do hash. But whereas if you do pickup 256 EBI and encode, every time you do one iteration, it allocates new memory. And memory in EVM is expensive. We have something called the quadratic memory expansion cost. So if you do this without using efficient hash leap, this loop is actually O(n) squared in cost. So you need to know what Solidity does under the hood, and you see whether Solidity has some functions to help you sidestep the overheads of Solidity. Another thing is that Solidity has some functions, some data types that make your life easier. For example, the dynamic array. One complaint many people have about Solidity is that it's not a very friendly language because when you allocate an array, you have to know the size ahead of time, like a ancient C. With Solidity, you can use this dynamic array and then just push, kind of like JavaScript or Python, just push. It will do the amortized resizing under the hood. And we also have like some high-level algorithms, like you can group sum, so you don't need to write your fancy loops. You can just call a group sum, and all these powerful expressive functions will hide all the complexity, all the assembly tricks in the background. You don't need to fast test them. It's already fast tested in Solady. Yeah, so if you know like what features Solady have and how to abuse them to the max, you can get pretty far. I would say you can get like ahead of 99% of code base out there if you just abuse Solady to the max without even writing inline assembly. Yeah, you can pretty much abuse, get ahead of 99% of code bases. So okay, after this point, I might talk about some principles or disciplines you have to keep in mind if you want to write Solady style code, which I think you don't really need to for most of the time. But if you want to be an optimizer, like show off your inline assembly skills, then you have to know a bit more stuff. So first, regardless, you need to be familiar with your tools, learn how to debug, profile, and test, like get comfortable with it. For debug, I would say you can use Foundry's debugger. You can use Remix. There's nothing shameful about using Remix. I use it all the time. you have to know how to profile. Like if you want to see the guess difference between two functions, you need to probably write two different contracts and then pass in the same inputs, because you want to keep the test as fair as possible. If you just declare two functions, and sometimes the guess is so small that the function dispatch might actually cost more than the function you're testing itself. So you need to get familiar with how to profile your code well. You don't need to remember everything. For example, if you want to use inline assembly to do your ABI encoding, you can use Chisel or force testing to see how Solidity does it. Then you try to mimic it, try to copy it using your inline assembly. And yeah, just remember a few things and figure out the rest on the fly. So if you want to dive into inline assembly, the first thing I would say is get very familiar with how Solidity handles memory, like the scratch space, the extended stretch space, how you can abuse 0x40 and 0x60 safely, and how memory arrays, byte structs, strings, how are they actually represented, how are they allocated. And you also need to know, keep in mind that when you go between regular Solidity and inline assembly, the scratch space and free memory might be dirty. The free memory pointer might not be aligned to 32, a multiple of 32. For example, if you ABI encode pack, it will misalign the free memory pointer sometimes. And you also need to be wary that the variables, for example, you pass in the uin160 or address into inline assembly, you need to be wary of the upper bits. They might be dirty. And if you assume that the upper bits are clean, sometimes weird stuff will happen, which can cause bugs. So you might want to know like where Solidity inserts hidden overheads. For example, if you use address.call, you allocate memory for the return data. If you use ABI decode, you also allocates memory if the decoding data has some dynamic types. If you use target.do something, this might perform a ext code size check, which is 100 guess, I think. Yeah, unless this function returns a variable, then it will use a return data size to check whether the contracts exist instead of using xcode size. Then you also need to understand the limitations of try, catch, all this stuff. And yeah. So how to build an understanding? I say if you really want to go into the details to get a very good feel, of course rescues is the one of the best goals too. But if you want to DIY your experience, you can read some Solidity contracts, study it alongside Soulmate or OpenSampling. I would recommend starting with examples like ERC20 because it touches events, it touches core data, it touches, I think, pre-compiles, it touches pretty much everything, like events, etc., etc. So I think ERC20 is like not too difficult to get an introduction. Also, it covers a lot of topics. Then sometimes if you see ugly code in Solady, you might want to question like why is the code written in this way. So sometimes I intentionally duplicate code because I know if I don't, the compiler might not inline it. Sometimes I write the code in a way that is not so optimized because I know that this function may be called once in a blue moon. So instead of making it like super gas efficient for runtime, and you bloat everyone's contract, you make everyone's contract like super big and hit the 24 KB limit, instead, all these rarely used functions, I might write it in a way that optimized for smaller bytecode size or readability. And sometimes I might consider what is the most often used scenario and optimize for that. For example, I think the enumerable sets, most of the time people won't store more than 3 elements in their enumerable sets. So I write the data structure in a way that it doesn't store the indices and the length until you exceed 3 elements. And you might want to study how other code base utilize Solady. So I think this is, wow, we actually only spent half an hour. Yeah, if you want to know more, you might use LLM assisted learning. There's no shame about it these days. Like if, let me see. Oh yeah, if you follow the developers on Twitter, sometimes due to the, like, we have to optimize for the Twitter algo. That's why we make our post a bit sensational. We hide information nuggets inside shit posts. Yeah. So you might want to use a LLM to make the learning curve more gentle. Or if you prefer like a more entertaining style, you can like see what developers post on Twitter. But then you will get a lot of shoes here and there also. Yeah. So I think that's pretty much it. Let me see any questions people asking.
So I actually do have a question, by the way. Have you been using any LLMs just to like optimize code, or do you even, as of now, do you use any AI tools to like write smart contracts or optimize it?
Oh yeah, I actually do, but I do it in a very old school boomer way. Um,
Mhm.
let me exit this screen so that I can go to Solady and show you
Okay.
the EV example.
Mhm.
Oh yeah, we're already in Solady. Okay, so are you able to see the screen? I'm sharing the screen right,
Yes, yes,
and
yes,
it's under
yes.
Solady. Okay, so let's go to one of the recent PRs. Shit, my computer is lagging. Please don't hang. Okay. Oh, luckily it's not hanging. Okay, let's go. Base 58. I think this is one of the examples where the LLM is pretty useful. So for example, okay, I tell you what is this PR about first. So base 58. Base 58. So Solana address, Bitcoin address, they use this encoding scheme called the base 58. Uh, yeah, basically base 58 has some kind of alphabets. Yeah, the alphabets are here. 1, 2, 3, 4, blah, 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 blah. Yeah, there's no I down here. The I is replaced by 1. There's no L. So we try to make it so-called human friendly so that people don't typos, and it ends up with this very compute unfriendly encoding scheme. And initially, the way to do this is doing it character by character, like you encode it character by character. Because to encode a base 58, you essentially have to do arbitrary precision integer math.
Mhm.
And the the implementation OpenZeppelin came up with at first is based off some Go implementation, which operates character by character. And I was like, this doesn't really use the EVM to the fullest potential. So the first thing I did is like I talk about the high level details with ChatGPT, and then I asked it to create a Python reference. Initially, I asked it for like 64 bits. Okay, I asked it to create a C reference first, a C reference using 64-bit integers, using 64T. Then after that, I asked it to uh, do it in Python using uint246, uint248 bits. Because, okay, 248 bits is the maximum number that can be safely multiplied without overflowing for base 58. So uint248 max multiplied by 58 will still fit under uint256. That's why I use uint248. Yeah, so I asked the ChatGPT to write in a language is more familiar in, which it has more data in, and then I asked it to tweak some parts such that I know exactly how to convert into inline assembly easier. Yeah, so the idea is don't directly ask your LLM to produce an inline assembly. It will probably fail, and it will probably make some hideous bugs that you cannot debug. So you start with something that is more comfortable in, and then you slowly shape the probabilities such that you nudge it towards. Uh, it's some I would say it's kind of like asking your intern to do step by step, and but if you think it in LLMs, it's kind of like activating the weights in a sequence that makes it more likely that you will end up with a nice answer, nice final result. So yeah, you create a Python pseudocode. After that, I convert it to assembly, and then I ask the ChatGPT to double check my work. I would say LLMs are very good at double checking your work, although they might make some false positives. I would say
Okay.
if you know what you need to look for, LLMs will be very good. So to a senior dev who knows like, okay, obviously this thing doesn't work because it will overflow. The LLM might not know it. It might produce some thing that will overflow it and don't realize that it actually happens because the LLM cannot simulate the compilation and the running of Solidity. So you have to look out for this stuff. If you know everything, you write it, then you just ask the LLM. Yeah, you can consider it like a person who helps you double check code, but then you also have to scrutinize what it tells you with what you know, because you know you have access to Foundry, and you know you have all this background information that you haven't communicated to the LLM, so you have more context in your head than what the LLM has. Yeah, so human LLM hybrid.
So don't really rely on the LLM. It's there just to like do a double check. You still need all those practices, all those optimization. But ChatGPT can help, or AI tool, any AI tool can like help you verify that.
Yeah, one thing one of
Mhm.
my critique about uh, like
Mhm.
agents like Claude is that you can't really guide
Mm.
the path, like the chain of thought. When you ask it something, it produces a chain of thought, but you can't actually say, hold on, I see you making some wrong move down there. Can I stop you and guide you through another path? I think it will be better. You can't do that, right? So
Mm.
I still prefer the old school way. Like you can really have a more hands-on how to guide the LLM towards the solution.
Mm. Okay, interesting. Okay, super cool. I don't see any questions in the comments as such, but do you have any example of like most optimized contract, like any DeFi contract, any NFT contract?
I think
Do you think?
Seaport is probably the most ridiculously optimized marketplace contract out there.
Which one?
Of OpenSea Seaport is the most
Ah, okay.
ridiculously optimized.
Oh,
Let me
okay,
see.
I see.
Okay, for Solady, okay, there are some contracts in Solady that I would say is quite evilly optimized. Okay, let's start with bytecode proxies. So for example, lead, where is it? Lead clone. So the thing about lead clone is that okay, let's start with lead clone first. Lead clone is a file in Solady that allows you to deploy minimal proxies. Minimal proxies, sometimes we call it clones. And these clone, they are kind of handwritten. Oh my god, my how to say this file is so big that the rendering is breaking. Okay. Anyway, let's go back. Yeah, I think this is jamming. Okay, so this stuff down here is the entire bytecode for the clone contract. You don't need to. Okay, this giant comment is just to explain how this how the bytecode works and the stack operations, so that you can manually trace through to see how it works. Then there are some stuff like signature checker. Okay, so we know that it is possible to handcraft bytecode contracts. So we push that to the next level. In signature checker date, we have this thing called ERC6492 checker. There is some contract down here. This contract is super ridiculous. Let me see. Okay. Yeah. Let's go to Etherscan first. Okay. I see. The computer is lagging. Open link. No, it's not a correct contract. It's going to hang. Okay, let me close the deep Chrome. So basically, this contract is another handcrafted bytecode. I would say it's not exactly fully handcrafted because I use U. U is like a dialect of, it's a restricted, I would say it's a sub-language of Solidity. It's an intermediate form. So I wrote the U code down here, okay. And then I use some, I actually forgot how I wrote this, but this contract is written in a way such that the code size is, I abused code size. Code size is the 2 guess of code. I abused it such that the code size is used as a variable for mstore. Yeah, what's this code size exactly? I forgot. But anyway, okay. Yeah, and in another thing is, I think there's an address somewhere. Address. Where's the address? Copy. Oh yeah, here 25, line 25. There's something called the address. if you go back to the Solidity iceberg, you see this contract totally hits a few of the lowest, deepest stuff. For example, 2 guess opcode abuse, create 2 address abuse, manual bytecode crafting. Yeah, it's one of the most ridiculously disgusting contracts out there. Basically, I use the create2 address to store the function selector required by the ERC1271 and somehow craft the contract to have a code size that that can be used as an argument. Yeah, this is I don't think you should really do this kind of stuff if you are not used to it. But this is once in a blue moon. You know that you only need to write this once, and I don't think anyone has to write it again. Yeah, it's still ridiculous.
Yeah, this is amazing. Any other DeFi contracts that you think of recently that you have been reading, or anything that you want to share?
I haven't been diving into DeFi like recently, so okay, most of my time right now is working on smart accounts, especially the Ithaca code base.
Yeah,
Yeah. So
interesting.
okay,
Actually,
Ithaca
I have
account is
something that.
kind. Sorry.
Yeah, go ahead. Go ahead.
Yeah. So I'm going to say that this contract, yeah, it abuses Solady to the maximum. Like, it's ridiculous. The amount of Solady abuse is quite heavy. Um, the reason why this thing is fast is because Solady is fast. Yeah. But there are some parts that we can't outsource to Solady. So some parts we have to write Inline assembly. And pretty much the storage in this account is very optimized. So we use Inline assembly for things like calls. Because when you call, maybe Solidity allocates memory in the background and perform all the redundant checks.
Very interesting. Also, I wanted to talk about CLZ opcode. So,
Oh yeah, the CLZ
let me
opcode.
switch my screen. Yeah, can you see my screen?
Wait, should I stop sharing?
Should be fine, but you can see my screen, right?
Oh, let me check your screen. Check your iPad. Oh yeah, I'm seeing your screen from my iPad. Yes.
So, what is CLZ opcode? I mean, a lot of people don't know it. So, just give a brief intro what exactly it is and how it's going to like optimize smart contracts.
Okay. Let's go. So CLZ is essentially a form of log2, log2 logarithm 2. It's not the limit opcode. It's the log2 as in math, base 2 log. Okay. I think it's somewhere here. Where is it? Libit. Yeah, libit. Let's see. So this thing is this is not CLZ. This is CLZ. So this chunk of code here is CLZ. What are the use case? Bitmaps, you want to find the next set bit. I think take math, if you have some something like a uni v3 or v4 and you want to find the next tick, you can use this thing. If you don't use this thing, you might write a loop, which is if else, which is not efficient, okay? It's not efficient. So this is like the most efficient way you can write it right now in Solidity. And there are some problems with this code. Okay, it's efficient. The opcodes here, yeah, is safe, is formally verified, etc. But the thing is, you see, these opcodes are big. So every time you call a CLZ, your contracts have to store all these junk, you know. And I would say it's pretty commonly used algorithm. For example, previously we talked about CD compress, using CD compress to compress your structs to store in storage. Let's go to deep-zip. Okay. Then I can show you a more practical example. For example, in Ithaca, we use CD compress. Yeah. To compress the struct such that we can fit into one storage slot. Essentially, we have CLZ in CD compress. Oh, wait. Shit, I forgot.
Yeah, your screen is visible.
Okay. Yeah, so CD compress here has count leading 0 bytes, which is a specialization of CLZ. Okay, because I know I don't need to count the exact number of 0 leading bits. So I count the number of 0 leading bytes, so I can remove a few opcodes. But essentially, I still have to do this all this fancy junk down here, which costs bytecode, you know. All this occupies bytecode, and people say, yeah, we are hitting the Spurious Dragon limit. It's because of all these giant magic constants, you know. All these giant constants, we are pushing the contracts, we are making the contracts fat. And all these cost gas. Every time we do this is another specialization. Is count the number of leading 0 bytes. Yeah, all these cost gas. So let's say if we have a CLZ down here, like right here, right now, if you have this magic opcode, we can throw away all these constants. Each iteration maybe will drop from drop by, I think in this case it will be around 100 gas. Yeah, each iteration will cost 100 gas less. And this thing can be so efficient that you might not want to manually pack your structs ever again. You might just call libzip.cd compress. In fact, right now, this is almost on parity with manual packing. Like maybe the overhead of calling CD compress is like a few hundred gas. I would say that's negligible compared to S-load or S-store. But with CLZ, this thing is like, yeah, it's almost no difference. It might be even faster than manually packing your structs.
Awesome. There is one question that I can see. What optimizations do you suggest for AMMs?
AMMs.
Yeah.
It depends what kind of AMM you have. Is it a CLOB or like that kind of that curve type? So it depends on what kind of curve you are using. Okay, first, your math libraries have to be efficient. I would say the fixed point math lib here is pretty efficient. And then I recall in Uni V3 or V4, they have all those giant magic constants. Those, I think, is pretty much, that part is pretty much optimized to the near the limit already. It's just that maybe some functions can be inline further. For example, if you call the CLZ, although I wrote it in like a branchless form so that it tends to get inline, sometimes the compiler just refuses to inline. And when the compiler refuses to inline, you will incur an internal function call overhead, which is like a push then jump and something. So depend on how many arguments, it can be around, I think, 60 gas, which is quite irritating. So for example, you want to call this 183 gas CLZ. The internal function call overhead is like 60 gas, which is irritating. Yeah, if you call it in a loop, then it will be even more uh, it'll be more irritating. Yeah, so you just I think you have to profile. It depends on your code base because depending on your code base, Solidity might choose to not inline some functions. Like if it detects, oh, maybe your contract is almost hitting the spurious dragon limit, I might not want to inline this thing. Yeah.
Hmm. All right. Other than that, I really don't see any questions in the comments. So I think we will wrap it up. But at the end, do you have any other tips or anything you want to conclude with?
Uh, I I would say that to get good, like super duper good, like top few percent good, you probably have to get some background knowledge. For example, this function I'm looking at, the lawn what, is by this legendary guy called Remco, and
Hmm.
there's a whole he wrote a whole series of articles on like how he used like Chebyshev approximation to come up with all this stuff.
Hmm.
Yeah, so if you want to like create new math, create new algorithms, you might need to go beyond knowing how to like abuse EVM outputs. You might have to like go to more traditional areas and then import the ideas from there.
Hmm. Yeah,
Yeah, like
thanks. In the comments, someone is saying that everyone's brain has now melted. So this was an amazing session.
yeah. So for example, wait, oh yeah, 6 more minutes. Okay, one recent function I wrote somewhere. What's the function? Shit. Let me see. Scroll down. Mouse square root. For example, mouse square root. Okay. Also called a geometric mean. So if your math is pretty like if you come from at least you didn't forget your undergrad math lessons, you might recall that yeah, if you want to find a square root, essentially this function is trying to find a square root of a 512 bit number
Hmm.
uh, to the accurate to the way. Yeah, the stuff here is really accurate to the way. Um, you have to do this thing called a Babylonian method. And the thing about Babylonian is that if you start at the overestimate, it converges super fast. But if somehow your initial guess is an underestimate, uh, it converges super slowly. So using this knowledge, you can like craft some very good heuristics that enable your starting guess to be very conducive to the Babylonian method. It's like knowing all these kind of like recalling what you learned in undergrad or probably in grad school. Yeah, it can help you quite a lot. Yeah.
Yeah, cool. Awesome. Then let's conclude the session. I hope everyone liked it. The recording will be available on YouTube, so you can like rewatch it. I will also upload it again on YouTube, so you guys can watch it. This was an amazing session, and if you guys are new to like the crypto ecosystem, you can go to Alchemy University. We have a lot of courses where you can just start learning and start building, and then at Alchemy, also, we have a lot of blogs on Solidity, on how to build on-chain applications, so you can check that out. And all the sources that also Vectorized mentioned in his presentation, you can check those out as well. Okay, awesome. Thank you so much, sir.
Okay. Thank you, Utam.